Hey everybody, welcome back. Today's lessons is going to be on 12.4, and this is the unit tangent, normal, and binormal vectors. We've been using so far IJK for our useful orthogonal vectors. For straight lines, it's our normal Cartesian coordinates. This is less useful along curves, but we still want a set of orthogonal vectors. And we will look at in 12.6 what this means in terms of physics. I discussed some of it with you in class today, but let's take a look at what we can use, and we're going to just jump right into it. We've talked about one useful unit vector already. It's the tangent vector. This was it. We talked about it in 12.3. The tangent vector is found by taking the derivative of r prime and dividing it by its magnitude. So all of these are unit vectors that we want. This vector is effectively the tangent line from that point at a given t naught. So we use it when we're finding it. We set t equal to t naught. We find what that tangent line is. This is the direction, forward direction, if you were a particle on that line and what direction you would be heading. It's your velocity direction, not magnitude. Velocity magnitude would be just r prime of t. We'll talk about that in 12.6 though. But we have that's only one of our unit vectors. We want one to cover 3 space, so we need 2 more. So let's go and motivate that. Recall in 12.2 we found that if the magnitude of r of t is constant for all t, then the dot product of the position vector and the velocity vector, r of t and r prime of t equals 0 for all t, and therefore they are perpendicular or orthogonal. And we're going to apply this to t of t. T of t is a unit vector, so the magnitude of t of t is constant for all t. It equals 1. So we can use the same rule. The tangent vector times the derivative of the tangent vector equals 0, and these are perpendicular or orthogonal, and this will give us another vector. So we have t of t. Let's find t prime of t, and when we do, we normalize it because we want to have normal unit. Normalize means divided by its magnitude, make it a unit vector. We make it into a unit vector, and this vector is called n. So t is for the tangent vector, n is for the normal vector. It's the principal unit normal vector. And now that we've got 2 vectors that are orthogonal, we can create a third vector, of course, using the cross product. This one is called the binormal vector, which goes by b, and we can do that with t cross n. Or optionally, you can do r prime of t cross r double prime of t, the second derivative of the position vector. So that's velocity cross acceleration. And then divide that by its magnitude to normalize it. This version of b of t is already a unit vector. T of t is a unit vector, n of t is a unit vector. The magnitudes are both 1. The outcome is going to be 1. This equation over here on the right isn't so helpful because we haven't found r prime, or the second derivative of r, and it's more work than we need to. In finding t and n, we already have what we need for b. Okay. So I want to explore this a little bit more with you. Like, what does this mean? If I have some curve here, and we're at this point, and I find that the forward motion of r is along that curve going to the right. The tangent vectors like that. There's a lot of orthogonal vectors. I could have straight up. I could have straight down. These others represent into the page at angles or out of the page at angles. It's like having a wire, and my vector can come out of it in 360. That normal vector is orthogonal in which way we go. So how do we know which vector is n? It seems like that's pretty important. Well, let's imagine writing t of t as in terms of cosine theta and sine of theta. And I got a picture of it right here. So we have our curve. The tangent vector is right there. Theta of t is the angle with the x-axis. Okay. If I take, making our tangent vector that, and taking the derivative, I get t prime is negative sine theta, cosine theta, and then times d theta dt. Okay. So what does that mean? We've got a couple options. If t is increasing, theta is increasing also. D theta dt is greater than 0. So as if we're going along it in this direction, as time with the curve that way, as time goes on, that angle goes like this, and it keeps getting steeper. So theta is getting sharper as we follow that vector along. This is the direction of t positive. Which means this whole thing is just as is. It's this is a positive value. Doesn't matter what it is. Positive 1, positive 10, they're just scalar multiples of this. They're all positive. It doesn't change the sign of these. So negative sine theta. Sine is positive here. So negative, my x component is going to be negative. So x has got a negative value. And my y value, cosine, is also positive here too. So my y has a positive value. The normal vector is somewhere going that direction. It's going inward like that in the xy plane. Notice there's no z component. So I picked a plane to do it in. And that's how it's always going to be. The normal vector points inward along a curve. Even in a three-dimensional space, whatever that plane is, wherever that curve, the plane of the curve is right there with t, the normal vector is going inward. And then we have the other graph. As t increases, theta decreases. So as time goes positive this way, if the angle is getting less, like this is t, but as we go along the vector, it's making a lesser value with the x-axis, then d theta dt is less than 0. And it kind of like sign-wise, it flips the signs of these. So negative sine theta is positive here. This made it negative. This makes it positive again. We end up with the equivalent of a positive sine theta here. X is positive. We do the same with cosine. Cosine's positive here, but now it's made negative by this d theta being negative. Whatever value y was, it's now got a negative scalar multiplier on it. So this ends up being y is negative. So x is positive that way, but y is downward. We have something pointing inward. The normal vector is pointing inward along the curve again. This happens in every case. N points inward along the curve. We will study curvature in 12.5, but it's good to know how that works. And then our third vector, what about b of t? We already know its direction. It's if we have t and n, we find the cross product. There's only one direction it can point. And as I was telling you earlier, the magnitude is already 1. So that's handy. We don't have to divide it by the magnitude of t cross n because of the cross product formula. Magnitude of A, magnitude of B, sine of the angle between them. Sine of the angle between them is 1. The magnitude of each of these is 1. B is a unit vector. Okay. So that's some interesting information. One more thing, one more idea thing I want to cover with you guys. Finding MT may or may not be easier than finding N of S, the arc length. Here we got to find R prime of T to get T prime of T. T prime of T, or T of T, is the R prime divided by R double prime. not double prime, r prime divided by the magnitude of r prime. Then we got to take the derivative of t and take its magnitude to find n. So there's a lot of steps there just to find n there. But when we're doing it with s, we use arc length rather than time. T of s is just r prime of s. And because we looked at in 12.3, the magnitude, when we studied arc length, the RDS, the magnitude of it is 1. And so this part is 1 down here. And so T of S is just R prime of S. Makes that a little bit easier to find. We don't need to find we don't need to take the norm of the vector. And so T prime, we can just go straight to the derivative, second derivative of R. And you will find that R T prime of S over the magnitude of T prime of S is the same as just doing the second derivative divided by its magnitude. So we can get away with a lot when we're working with S. Everything's a lot quicker. So we just take the derivative of R twice and we don't have to calculate T prime. T prime just kind of falls out for us. Okay. Then when we're also working with S, B of S, we have this formula. We can still do T of S cross N of S. We have that already. Shifting to the version that had R cross double or R prime cross double R prime, R double prime divided by its magnitude. Well, this just turns into this because the magnitude of R prime of S is 1. The bottom here is just R double prime of S, the magnitude of it. We've already calculated this when we did T. So all you need to do is R cross R double prime and divide by this, and you're done. You don't ever need to find N of S or T of S directly. You can still do that version, but I think this is a lot less work. All we need to find is R. We have R. We need the first derivative, the second derivative, the magnitude of the second derivative, and that's kind of it. The only other operation we have is a cross product. So if you have arc length, or arc length is easy to get, it can make less calculations. That's it for this starting section. Peace.